Good morning, friends. Our last class was about back bondings. Now we'll apply this concept of back bonding to some given molecules. Back bonding. Okay. So let's take the example. Suppose you are asked to compare the concept of Lewis acid character. There are the molecules SiF4, SiCl4, SiBr4 and SiI4. So what is the concept of Lewis acid? What do you mean by Lewis acid? We know Lewis acid and Lewis base. Lewis base can easily donate an electron pair and Lewis acid can easily accept an electron pair. Okay. So among the given molecules, which has the highest Lewis acid character and which has the highest Lewis base character? Here you see, here the silicon and fluorine, silicon and chlorine. Obviously fluorine, chlorine, bromine, they should be the donor atom and silicon is the acceptor atoms. But here we will not consider the concept of back bonding because here silicon belongs to the third period. So here though back bonding is possible but it is not so effective. So that's why forgetting the concept of back bonding will decide the Lewis acid character. So then how will consider the Lewis acid character? You see here silicon is the central atom and fluorine are the peripheral atom. The electronegativity of fluorine is more than the chlorine, bromine, iodine. So if we write down the electronegativity value, fluorine has more, then chlorine, then bromine, then iodine. That means fluorine will attract the electron pair towards itself with greater energy than chlorine, bromine, iodine. So that's why now here the silicon feels more scarcity of electron than this molecule, than these molecules. So in other way we can say here SiF4 silicon can easily accommodate or accept the electron pair from other sources. So here SiF4 is the strongest Lewis acid and the order will decrease like this. Okay, so we can say SiF4 is the higher, more powerful Lewis acid than SiI4. Then we come to the example number 2. Example number 2, AlCl3, AlBr3 and Li3. Same concept here. Over chlorine, bromine, iodine, the presence of lone pair and aluminum has the vacant orbital. So its back bonding is though possible, it is not so effective. So we will not consider the back bonding concept here. So forgetting the concept of back bonding, only based upon the electronegativity concept we will decide the Lewis acid character here. So we know which can easily accept the electron pair is the most good Lewis acid. So here chlorine has the higher electronegativity then bromine, then iodine. So among the three molecules, the scarcity of aluminum, the electron scarcity over aluminum is more due to the higher electronegativity of chlorine. So that's why it acts as a good Lewis acid than the other. So the Lewis acid strength will vary in this order. This is the least and this is the highest. Okay. Now we will take the example number 3, BF3, BCl3, BBr3 and Bi3. Here central atom is the boron. This is the acceptor atom and fluorine is the donating atom. Here also boron is the acceptor. In all the case boron is the acceptor atom here. Here back bonding is possible and here boron belongs to the second period. So here effective back bonding is possible. Here the back bonding is very good due to the very fantastic overlapping between the orbitals. Here back bonding takes place between the 2p of boron and 2p of fluorine. So it's the back bonding versus 2 and 2. So it's a very effective back bonding. So in this case we consider the concept of back bonding, and accordingly we will decide the Lewis acid character. So back bonding will be more in case of BF3, then BCl3, then BBr3 and BI3. If we will consider only the concept of electronegativity, then as fluorine is the highest electronegative element, so it should be the good Lewis acid. But due to the concept of back bonding, we will not use the concept of electronegativity value here, only we will consider the back bonding. So here as BF3 the back bonding is more fantastic, more good. So that's why the scarcity of our boron is somewhat reduced due to the donation of lone pair from fluorine to boron. That's why here BF3 cannot be a good Lewis acid. So the pattern will be reverse. So here Bi3 will be the good Lewis acid, then BF3, unlike the other two examples. In the above two example, we put the concept of electronegativity value, and in this example we put the concept of back bonding. So we have to be very careful whenever we are given any examples to compare the Lewis acid or Lewis base character. First of all, we have to see whether there is any effective back bonding. If any effective back bonding is there, then you consider the pattern depending upon the back bonding, and whenever there is no back bonding, at that time you arrange the pattern depending on the electronegativity value. Okay, now come to the next example. PF5 and PCl5. PF5 and PCl5. Are you getting my points? So one thing, you consider it properly. Okay, so is there any back bonding between PF5 and PCl5? No, because here phosphorus belongs to third period here, so there is no effective back bonding. So here we will not consider the concept of back bonding, only depending upon the electronegative value we have to consider. So fluorine is more higher electronegativity value than chlorine, so that's why PF5 is the stronger Lewis acid than PCl5. We will take one more example, CCl4 and SiCl4. Now what happens? In CCl4, already we have discussed in the last class, chlorine has the presence of lone pair, but unfortunately carbon has no vacant orbital to accommodate this lone pair. So here no back bonding is possible. In SiCl4 also there is back bonding, but it is not so effective because it belongs to 3 and 3. That means silicon belongs to third period and chlorine also belongs to third period. So here no effective back bonding. So we can say here also no back bonding and here also no back bonding, not so effective back bonding. Now we have to consider the Lewis acid character. Are you getting my point? Now we have to consider the Lewis acid character. That means this molecule and this molecule, when they can accept the electron pair from the other given molecules. Okay, suppose it's the molecule NH3 and it is BF3. Okay, so here BF3 acts as a Lewis acid and NH3 acts as a Lewis base, because it can given the lone pair to boron, because here boron has the vacant orbitals. Are you getting my point? So if it acts, in order to act as a Lewis acid, so it has some vacant orbital, but in CCl4, there is no vacancy of orbital over carbon, so it can never accommodate the electron pair. But in SiCl4 there is the presence of vacant orbital, so it can at least accommodate the electron pair. So based upon this concept we can say SiCl4 is the good Lewis acid than CCl4. SiCl4 is the good Lewis acid than CCl4. One more example we will take. Suppose PCl5, SiCl4, AlCl3 and SF6. Here they belongs to phosphorus, silicon, aluminium, sulfur. Here they belongs to third period, so there is not so effective back bonding, so we will not consider the concept of back bonding here. You see the oxidation state here, sorry, here +5, here +4, here +3 and here +6. So if you will see the oxidation state over silicon +5 and over phosphorus it is +5, over silicon over sulfur it is +6 and over phosphorus it is +5. So when there is more positive charge over a central atom, it will, that means, can attract the electron pairs or bond pair with more energy. So it has the natural tendency to accept the electron pair with a higher force, so it should act as a good Lewis acid. So based upon this concept, PCl5 is the strongest Lewis acid than the other, but one exception is here SF6. Why I put SF6 in the last? Because here the oxidation state of sulfur is +6, it should be the more electron capacity, that means SF6 should be kept in the first than the PCl5. Why I put SF6 last? Because here some other phenomenon is occurring. If we will see the geometry of SF6, it is octahedral geometry, so it cannot elect, so there is more steric crowding over the sulfur atom due to the 6 surrounding fluorine atoms, so it cannot easily accept electron pair from some other molecule. That's why it cannot act as a good Lewis acid. So that's why I put SF6 last in this series. So the Lewis acid strength will be like this, and just we will take 2-3 more molecules for deciding the Lewis base character. Lewis base character takes the example of NF3, NCl3, NBr3. Okay, so what is Lewis base? Lewis base should easily donate an electron pairs towards the other molecules. That means whenever the electron pair is easily available, that means it can act as a good Lewis base. First consider the case of back bonding. Is there any back bonding in this molecule? No, because you see over the nitrogen there is the presence of lone pair, over the fluorine also the presence of lone pair, but which can accept, which can donate? Because if fluorine is the highest electronegative atom, so it should accept the electron pair from the nitrogen, but fluorine has no vacant orbital to accommodate this electron pair, so it cannot act as the acceptor. So and here also not possible. Okay, NF3 and NCl3, okay, and NBr3. So we will not consider the concept of back bonding here, only based upon the electronegativity concept we will decide. In NF3, in the lone pair of nitrogen more attracted by the fluorine negative fluorine atoms, that's why it will be the least Lewis base, and NBr3 will be the highest. So Lewis base character vary in this way, it has the highest and it has the lowest. Now you concept come to the example NMe3 and NSiH3. Here with nitrogen 3 SiH3 groups are there, and here 3 methyl groups are there. Here over nitrogen lone pair is present, but in this case here carbon is present, carbon has no vacant orbital, so it cannot accommodate the electron pair present over nitrogen. So here no back bonding, but here there is the presence of back bonding. Okay, so as this lone pair participate in the back bonding, so this lone pair is no more available freely for this donation to other molecules. That's why your Lewis base character decreases. So in this case, NMe3 will be the good Lewis base than NiSiH3. Come to the last example, PF3, PCl3 and PBr3. Okay, here fluorine has the lone pair over phosphorus and lone pair over present over phosphorus. In fluorine also there is presence of lone pair. So at the electronegativity of fluorine is more, it should accept the lone pair from phosphorus, but it has no vacant orbitals. So easily we can discard the concept of back bonding here, and again phosphorus also belongs to third period, so we will not consider the concept of back bonding here. Directly we will go to the electronegativity concept, and accordingly the electronegativity concept, fluorine has the highest electronegativity value, so that's why it will attract the shared pair of electrons present over it will attract the lone pair present over phosphorus with greater force. That means its Lewis base character decreases, so it will follow this trend. Here PF3 will be the least Lewis base and PBr3 will be the strongest Lewis base. That's all. So in this class we discuss some molecules where back bonding concept is applicable. So the fundamental line of this discussion is that whenever we are given some molecules, first of all we have to see whether the back bonding concept is applicable or not. If the back bonding concept is applicable, then we decide the Lewis acid or Lewis base character depending upon the back bonding concept. If back bonding is not there, there is no effective back bonding, then we have to decide the pattern as according to our usual knowledge, that is electronegativity value, inductive effect, all these things. Okay, that's all. Goodbye.